You are in the lab and see in front of you a hollow cylinder spinning with lowercase omega equals 20 RPM. You decide to drop the solid cylinder on top of it. What is the final omega after you drop the solid disk? As we examine this problem carefully, what we see can most easily be described as a collision. A moving hollow cylinder comes in contact with a non-moving solid cylinder, and afterwards the two act as a single object moving with a single omega. Described in terms of a collision, we could say that the two objects, since they stick together, are suffering a totally inelastic collision. However, since neither one of them has a linear velocity v, rather than this being a linear momentum problem, this is an angular momentum problem. The style with which we solve an angular momentum problem is very much the same as the style with which we solve a linear momentum problem. We set the angular momentum at moment 1 equal to the angular momentum at moment 2. And in this problem, since there is no external torque, we have the case of conservation of angular momentum. We realize our angular momentum equation by summing the angular momentum at moment 1 and setting that sum equal to the angular momentum at moment 2. As is our habit in all problems where there are multiple objects, we'll use the case of our variable names to indicate which object we refer to. The hollow cylinder, since it has the smaller mass, will go by lowercase letters, and the solid cylinder with the larger mass will go by uppercase letters. So, at moment 1, we ask ourselves whether the hollow cylinder has an angular momentum. The answer is yes. Its moment of inertia times its omega at moment 1 is its angular momentum. We ask ourselves at moment 1, before the two have collided, whether the solid cylinder has a moment of inertia, and the answer is no, because it isn't yet turning. We complete the equation by considering the two objects to be a single object in the second moment, and we ask whether that object has an angular momentum. The answer is yes. Its total moment of inertia will be lowercase plus uppercase I, and its angular velocity will use uppercase omega subscript 2. In this expression, we need to substitute for the moment of inertia of each of the two objects. Lowercase I is the hollow cylinder, whose moment of inertia is its mass times radius squared. And the solid cylinder has a moment of inertia equal to half its mass times the radius squared. Although it wasn't specified in the original problem, we must assume that the two radii are the same in order to get a simple solution. Doing so, we get the following result. We first notice that the radii will cancel at all points in the equation, producing the simpler result. 1.5 times 20 RPM is 2.5 times omega 2. We recognize that RPM, which stands for revolutions per minute, is not our preferred unit for an angular velocity. However, the symmetry of this equation, having an I times an omega on each side of the equal sign, means that we don't have to convert the units. If we're comfortable getting omega 2 in RPM, we can simply cancel the units as they are and get the following result. Omega 2 is 12 RPM.